And I guess I better start this morning by recapitulating a little bit where we are. But the main theme for today in the 4 lectures will be the guts of TeX, the inner parts that really do most of the processing inside. And tomorrow's theme is going to be the things that are going to be of primary concern to people in this audience, what they really want to know about the things that are going to be slightly different from one place to another. So to remind you of this, of the structure of TeX itself, somebody asked yesterday, could they have a copy of this diagram? And so I've made up Xerox copies, and we'll pass these out now. Start them going in 2 directions. So we can get a feeling for where we are. Now this is, remember that I said this part was the code. And each box represents about 10 modules in your listing. So when we were talking yesterday about the dynamic memory in the last hour, this represents the amount of code there was for the dynamic memory, but the dynamic memory itself was taking a lot more space that might overlap this whole diagram by at least half of it, but maybe all of it for the dynamic memory itself. Then the EQTB, the equivalence table, is what I call locals here. This is the part of the program that refers to saving and restoring the equivalence and defining all the macros that we had for equivalent. In the first lecture that we're having this morning, I want to study this part, syntax, which is the part of TeX that reads the input and figures out what to do next. Then next hour we'll be talking about semantics, which is doing it. Okay? Any questions on what we're about to do? So then we'll go back and take a look at that listing. So certainly I can't cover all of the ideas of syntax in 1 hour, but what I want to do is give you the feeling for how it's organized, so that if you have any particular question on it, you know exactly where to look. And the sections on syntax start out with Part 21, Module 277, Introduction to the Syntactic Routines. And then that carries on through Part 27, Building Token Lists. So the basic scanning subroutines, Part 26, is the bulk of the thing. That's about 55 modules worth in that section, and I'll probably talk a lot about basic scanning subroutine. Since I can't cover everything, the approach I usually take is trying to do a sample, a random sample, study the whole thing lightly and one thing in depth, and thereby get some idea. I'm not sure which one to study in depth, and maybe I can take some suggestions from the audience as we get into it. But first we should start out just with the basic idea of syntax, what we have to do. The goal of syntax is to deliver is to scan the input and deliver the necessary information to the semantic routines. And at the level the semantic routine wants it usually wants to get a command and a modifier to the command, which is called chur. Although chur sometimes is a pointer, not really a character. So we have a command code and a character part, and then there's also CS pointer goes with it in case the thing that you fetched from the input was a control sequence. Then the command will maybe be the CS pointer will point to whatever control sequence actually had this command in chur, so that in an error message, for example, you'd like to use the control sequence that actually caused this thing. Somebody in TeX can say let \A equals def or something like this. Well, now if I have what, if you've decided to redefine text primitive called def, and the user is using some other name for it, then you have an error message. You would like to use the new name in the error message rather than the old one. So CS pointer is another thing you get from the input routine. So the thing that delivers the next token is called get next. Subroutine get next. And its job is to get the next token of input. Now, might sound like an easy job. After all, you just advance your pointer 1 in the buffer, and there it is, right? However, get next turns out to have a lot of different things that it might be having to get. For example, it might have to expand a macro. It might have to be reading an argument on macro. It might have to recognize a control sequence, whether it's defined or not, and look it up in the hash table. It might find that in order to get the next thing, actually we have to prompt for it because it hasn't been given to us yet. We might run to the end of a file, so if we get to the end of the file, that means that we have to close out that file, do some processing. All kinds of things can actually happen when you say get next. Historically, in fact, get next was the routine that started this whole web project going. We took the get next procedure out of TeX82, and we said, well, how would we really want to present this code? And we played around with Luis and I, tried several drafts until we had played around until we got to what we thought would be a good way to present the get next routine, and that led to the doc system of 2 years ago, and eventually to web. So it had enough structure and subparts to it that it was really our first test case for the whole idea of this style of documentation. The get next routine it begins in module 317, and the structure of it is given there. So the get next by itself looks very simple. Let's see if we can focus on this. Can you read that with your TV with your camera? Let's try to see if we can set up the way we had yesterday. Okay, you need enough light on my podium in order to read to see where my finger is. But then people on the screen could see where I'm pointing if they project onto the screen what's going on the monitor. It worked yesterday, but it might take a little bit of figuring to do it here. Now I got something on the screen here, and I'm pointing to get next. You can see a finger? Yeah. Well, is that about all? Okay. Somebody said that they could shut the door back there, and that would make it easier to read the screen. No? Yeah. Okay. So the whole idea of get next is rather simple. Then we have a couple of labels in here. Restart. If for some reason what we tried to get resulted in nothing, and so we have to start again. Then there's some other switches that we go to. But the code for get next is very short, except that it involves a couple of submodules. So we set CS pointer to 0. CS pointer is going to be 0 unless there was a control sequence gotten. That's why the EQTB starts at location 1 instead of 0, because the first control sequence actually is 1. Then state is one of the variables that we have set up for us all the time at our fingertips to tell us what kind of input we're doing. If the state is token list, that means that we're getting something not from the user's source file, but from inside of TeX, from some token list that we have to read through and get the next symbol off that token list. The token list can be of about 10 different kinds. the for example, it could be an output routine, it could be a macro, it could be every par, this feature that comes up at the beginning of a paragraph. It could be the parameter to a macro. Could be something that we inserted just to back up. We read some token. We decided we weren't ready for it now, so we put it back and into a small token list, and so that we can read it again. It might be something like we converted a number to Roman numerals, and we want to read that. So anyway, token list is one way we can get input. But if it's not token list, if the state is not token list, then we get input from an external file, and we would go to restart if there wasn't anything found. Otherwise, we of course want an input from a token list, and we have other cases where we might have to go to restart because there was nothing there yet. So two main branches of getNext for those two cases. Then if we've got to the end of an alignment entry, then we have to do something special for alignment. Here's one of the places where this post-hypnotic suggestion comes in with alignment, saying that, for example, if you just now got to a tab mark in alignment, this is the time to emit the thing that's supposed to finish off that column. And so you do a little bit of special calculation for alignment if you just happen to notice that if it gets triggered right here in the middle of getNext. Now, getNext is part of the inner loop of the code. Certainly, when the first part of it here, this restart, CS pointer to 0 and so on. And I talked a little bit about inner loop yesterday. Now, if you want to find out exactly where I think most of the time is spent in TeX, you look in the index and under inner loop, and it refers you to about 20 modules, which I believe are the ones that account for almost all of the processing time, in the sense that the other ones are probably executed an order of magnitude less. And not all of these modules are executed very often, but so we try to write the program so that the frequent parts are done rather fast. And I think my estimate is something like 100 machine instructions per character of text is approximately right. I have to double check it again now that I've got the whole text put together. But that was, if you consider what would happen if you took a TeX file, added one more character to one of the paragraphs, how many more machine instructions would the CPU have to do? And it was on the order of 100, I believe. And we tried to keep that going fast. So we want getNext in particular to be reasonably fast. And if we're inputting from an external file, we go to module 319. Module 319 is a switch that we're reading from an external file now. So our state, actually, the state consists of a number of different things. 5 or 6 different quantities that actually correspond to the current input state. And one of them is called state, which we looked at to see if it was tokenless or not. Another one is called loc, which is the location where we are in the buffer. Another one is called limit, which is the end of that line in the buffer. In the buffer, we might have lots of different lines. We might have part of a line from a terminal. We were reading some file, and in the middle of that line it said input from another file, and so we might have several different things in the buffer. And limit tells where the current line ends, and if it's a local less than or equal limit, then current line is not yet finished, and so we have to do the thing that we're almost always doing. When the loc is greater than limit, though, then we have an unusual case, not in the inner loop, and that is move to the next line of file or go to restart if there is no next line of the file. And so we do that, and that's a time when we can also check an interrupt. There's a provision, if you can do it in your system, for interrupts, for interrupting TeX. And at safe times to make an interrupt, I'll say check interrupt. There aren't that many places where I do it. But this is a fairly good place at the end of a line in the buffer. So that if you at the end of a token list is another place, and this happens fast enough that if somebody's sitting there and wants to stop the TeX run or do something special, you can probably catch it in one of those places. Now, The main case, though, the one that we want to be at high speed, is this first line here, where loc is less than or equal limit, because that's the case that we're most interested in getting to go fast. Okay, so then we set current char to buffer position buffer loc. So buffer is an array of ASCII code characters. This is TeX internal code, and all the external file has been converted to that and sits in the buffer in internal code form. Increase the location, and then we go to set up the current command, which is the chcode of the curchar. Now, chcode of curchar is really, this is a macro that's an abbreviation for get out of the EQTB the current value of the chcode for that character. We have made sure elsewhere that this is going to be in range. Nobody's allowed to store into that part of EQTB a number that couldn't possibly be a chcode of a character. I think the legal ones are 0 to 15. So this is known to be, current command is now known to be a number between 0 and 15. And then we have the big thing that changes state and go to switch if the current character should be ignored. So now in the TeX manual, I have a chapter that sort of says what these states are and how we're actually reading. So we have a state that says we're skipping blanks. If we're in skipping blanks state, then if a blank comes next, we skip it, and so on. There's 3 states actually: midline, new line, and skipping blanks. And we want this to be fast, so that's module 320. Let's take a look at what that is. So module 320 is a big case statement, and it's done by case of state plus cur command. So the state is now encoded as a number that is 1, 17, or 33, I believe it is. So that the current command, being between 0 and 15, added to the state, will take us to a unique location. No sense multiplying here. We're in the inner loop. We might as well define the state code so that it already includes the multiplication by 16. So then we can have a state various states like, well, here's an example: midline plus spacer, midline plus carriage return, skip blanks plus carriage return, any state plus end line. Any state plus is a macro that's defined it's defined over here. Where was it? Here. Any state plus. Can anybody? Yeah. Any state plus midline. So that adds midline plus the thing, skip blanks plus the thing, new line plus the thing. So anyway, this is the way we recognize it's a 48-way switch that will at high speed decide what to do next. If, for example, we get any state plus escape, we have to scan a control sequence and then set state to skip blanks, because we're going to skip a blank after a control sequence. That's the way this part of the code looks. And the number of machine instructions actually needed for this is supposed to be rather small. If your compiler really does terrible things with case statements, then you might want to take the few places in the inner loop where there's a case statement and do something special to that part of the program. That as a refinement, but it will make TeX run faster. If you can make this part run 5% faster, your TeX will probably run 4% faster. So something like that, I think, is worth pointing out. Now, if you have a token list, that starts at module 333, and so the token list, again, we have state information besides the state. The variable called state itself will equal token list, but then loc in this case will be a pointer to what token is next in the memory array. And if that's null, then we might, we're at the end of the token list. But if it's not null, then we fetch out of the token the command and char and CS pointer, just as if we had scanned it out of the input. And otherwise, if it's null, then again we have one of these things where we can end a token list. I thought that I I guess n token list itself is where it would check for an interrupt. Okay, and I am surprised I don't see a pause for interrupt in there, but I suppose it's in n token list itself. I don't want to take time to look it up now. One thing I wanted to mention about this is that you'll notice then the control sequence it doesn't live in mem by its alphabetic name. The only control sequence is represented as an address in EQTB in that token, and so the only time you're ever looking at a control sequence to figure out what its hash address is when that appeared in a file. The only time you are scanning, you have to compute a hash code to figure out where the EQTB address is in the first case of getNext, where you saw an escape delimiter in the file. So if you have a long or short macro name, it doesn't make any difference when you're actually using the macro as to how long the name was. It only took a little longer for a long name at the first when you input the thing into a token list in the first place. But once you've got a control sequence into a token list, it's just like any other control sequence, no matter how long its actual external name was. Okay, so all of these modules handle then there's weird cases of getNext where we have to do things like a person has said pause, set to non-zero value, and in that case that means that after you've read a new line out of your file, you're supposed to display it on the terminal, give the user a chance to see what's going on and maybe make a change to it before TeX actually gets it. You have to, and in my change file, the only thing I had to change in getNext was to make it more friendly on our particular editor at Sale, which is page-oriented editor. So we have not only page numbers, line numbers, but we also have page numbers. So I had to make sure that that the page number would get adjusted when I passed a page mark in the file. Also, I spent most of an afternoon trying to get it to work with our line editor, which is a special feature on our system that allows a user to change a line as it comes in and edit it with some rather powerful editing commands that will search for characters and insert characters in the line and so on. And I made this part of the getNext routine talk to that system routine. So it's certainly not standard in Pascal. So I had to do those two things in the change file for getNext. Now almost all uses of getNext are covered in the next part of the program there, starting at 338. And the most common way to call getNext is get NC token. If you look at the rest of TeX, you'll find, and you find out where is getNext actually used. You think, well, this would be one of the most common subroutines to call because you need to get the next token in a lot of different places and continue on advancing to do something. But if you look in the index under getNext for the uses of it, you find that it's only used in about 4 places. But it's used in get NC token, and most of the other times in TeX, when we want the next thing, we actually call this subroutine instead of the other one. The only exception to that is, the only place where the main body of TeX itself calls getNext is in the inner loop, where we want to avoid an extra level of procedure overhead of get NC token. And so in the very inner loop, where you're scanning a word out of a paragraph and looking for ligatures and things like this, where you expect that the next thing is just going to be a letter, then you call getNext in order to avoid get NC token. And then if you look at it and it looks like it's something that's more complicated, then we'll call a subroutine and leave the inner loop. This inner loop the idea of making it efficient has affected the coding to a certain extent. It makes it a little harder to read, but I think only 1% harder, so it was okay. Now, get NC token is like get next, but it does more. NC stands for non-call, and call is a macro that has to be expanded. So get NC token means that if it's get next, but if it turned out the next thing was a macro, expand it and get me the next thing that isn't a macro. So so when I call get NC token, this says let me see whatever is next, but be sure that it doesn't include any control. It's not something that's been deffed. Furthermore, get NC token sets, besides command and char, in fact it's called cur command and cur char are the variables that get next then. It sets cur toke, which is a token, a half-word representation of the command and char and CS pointer, so that you can have one variable that stands for all of the others in a packed form. This is convenient if you want to store it away in another token list or something like that. You can use it, or if you have to back up, it's all ready to be backed up. So get NC token gives you the values of cur command, cur char, CS pointer, and cur toke, and this is enough by itself to deduce the other three. Get NC token will also expand not only macros, but it will expand marks like top mark or something like that if you want to, because they're somewhat analogous to macros. If the next token is an undefined control sequence, get NC token issues you the error message saying undefined control sequence, because this is where it would not let it get through. When you call get NC token, you don't have to check afterwards that the thing was an undefined control sequence. Get NC token will already remove all undefined control sequences from you and get the next thing that's really legitimate. There's another routine called NC token I might just mention, because it's used only in the one place in the inner loop, where in the inner loop we had a place where we expected that it was unlikely we'd have a macro coming next. And so we called get next. It was going to save us the level of procedure call that would have said call this first, and then that would call get next. This would be a little faster. But if we found out that our assumption was wrong, that really there was a macro there, then we call NC token, which is exactly the same as get NC token, except that somehow get NC token is equivalent to get next followed by NC token. The other main way to call get next is called get token. And this one does not expand macros. It just gives it to you with so the token that you get your cur command, you get your cur char, and your CS pointer, and you get cur token also. But it's possible that cur command would be call or long call for calling a long macro, or something like a mark, top mark, or an undefined control sequence. It's certainly possible that get token will return you the name of an undefined control sequence. And this is the thing that you use at times when you're building a definition. For example, after the word def, and then if you say def whatever follows it, you'd say get token. You certainly wouldn't want to say get NC token. That would replace a thing by its previous definition or give you an error if it wasn't already defined. It would be a big tragic mistake. So there are places where we definitely want to suppress macro expansion, and that's what get token does. Okay. So those routines, get token, get NC token, they're rather simple routines. Module 339 is get token. Just to reinforce it, let's show you what get token is. This is module 339, and it says set cur command, cur char, and cur toke. I goofed. I said Kurt token on the board here. I meant Kurt toke. Okay, there's a no new control sequence is set to false, then get next and set no new control sequence true. The in the middle of the get next routine, there's a part of it that would have to look, that might have to go and look at the hash table and add a new undefined control sequence to the hash table. Now we don't want to put misspelled things in the hash table if they're going to turn out to be an error. So generally we have a variable no new control sequence that says new control sequences aren't allowed. This is the only place where we set it false and we set it true afterwards. Now this violates prevailing wisdom about programming, which says that you shouldn't, that global variables are considered harmful, and that you should pass such things as parameters. But my comments about the inner loop should indicate why I feel that this is actually, as long as we're using it in a disciplined way, we know what we're doing. This is a valid way to save a lot of time by not saying get next of some parameter that says whether or not a new control sequence is allowed or not. And get next would have to propagate that down to the hash routine and a bunch of other things. Setting up a parameter every time we call that subroutine would make TeX run a lot slower. All right, so get next, this will then allow a new control sequence to appear. I guess I made a little lie when I said that's the only place this is set false. There's one other place, and that's in any TeX when you're first loading the hash table. Okay, then if CS pointer is 0, this means there was not a control sequence found. Then we do this part. Otherwise, we set current token equal to the CS token flag plus CS pointer. So current token is properly set up, and that's all there's to it. But if it was 0, then there's a fatal error in here if the current command is NV. NV occurs in alignment, and this would actually be something I'm not even sure can ever happen. But probably it will. But if it would happen, I wouldn't have any idea how to recover from it. And this would mean that somebody is calling macro without expansion at a time when it's also possible to be finishing a column in an alignment. And well, if you think about it a while, I think there's nothing else to do except give a fatal error, and we'll see what happens if there is ever, if that turns out there's a way to recover in a reasonably common case, and of course we would change this part of the code. So I'm going to make the check here, because if I didn't and I allowed that NV to get through, then all kinds of things could screw up in the rest of TeX. So I wanted to trap it here. Even though this might be the inner loop. And curtok then is set in this case to a packed version of the command and character. As we mentioned yesterday, that's the way we represent a token. All right, those are the basic things that all the rest of TeX relies on: get token, get NC token, in order to look at its input. Any questions on that? Okay. Now the interesting part of syntax is a section called basic scanning subroutines, and these are the things that do higher level parsing of text sources. And well, basic scanning routines start out with some that are actually pretty dumb. There's one called scan left brace. Every once in a while, TeX gets to a point where it's got to see a left brace or not, or else it's stuck. And so it calls scan left brace, and this subroutine, I think it's probably used about 15, 20 times. This is module 363, so it just this is the typical way that we will call something, and it says get the next non-blank non-call token. If the next thing is really a space, then we won't give an error message saying missing left brace, because we'll keep on going until we get something besides a space. But then, so this is a little thing that gets used very often. Notice module 364. This code is used in sections 363. rather often we'll say get NC token until cur command is unequal spacer. Okay. And then if cur command is not a left brace, then we got this long message, and here it gives us a chance to show how those help messages and errors are. A typical error is done. Fatal errors are very unusual, but this kind of error where we give a help message is typical. So take a look at it. If we start out with print something on a new line, and our error message, our official error message here, starts with an exclamation point, missing left brace inserted. Now, the help message is given next before I call the error subroutine, and the number of lines of help is used here so that I could stick to simple web macros, and so I have a help 4 for a 4-line help message and a help 3 for a 3-line help message, and so on. The help message comes in, a left brace was mandatory here, so I put one in. You might want to delete or insert some corrections, so that I'll find a matching right brace soon. If you're confused by all this, try typing I right brace now. That's the best way to probably recover if they didn't. But if they had a missing left brace and I'm going to put one in, it can also be a problem if there isn't a right brace somewhere else. Then I call back error. Back error is something that takes current token and puts it back so that it'll be read again. And so the next thing get token or get next we'll see is the one that it just already saw. And it backs up and also does the right things for backing up. And then the current token is set to a left brace token, and we pretend that we've read it. That's in agreement with what we said here, that a missing one was inserted. Somebody asked me the other day why the style of these help messages using I and you in these messages, and I believe there's several reasons why it turns out to be a win to have the computer talking to you as if it understands. I mean, or it'll make a statement like saying, I don't understand this, or I do understand something, when we all know that the computer doesn't really think. Well, because the main reason is that you can communicate a lot more in a small space when you use the English language the way it was designed to be used. And English language has developed over thousands of years, and the thing it's most powerful at is discourses between people. And so if we restrict ourselves to using third person all the time, then we're losing a great deal of power of it. So in fact, I sketched out all kinds of ways to write help messages, and finally this one turned out to be by far the one that gave the most had the most effective. I'm quite convinced of this. Now the help messages have to be at most 60 characters long per line. And I also like to make those lines break in a somehow fairly nice way. So it was a little bit of a challenge sometimes to take a 61 character one and figure out what was the right word to substitute. But when writing these help messages, I also tried to use words that were different from the ones in the official error message that was given earlier, so that person has the error described in 2 different ways, has a chance of understanding one of those 2. Now, if people here from foreign countries implementing TeX there would like to make TeX more friendly there, you might probably be better to have the help messages translated into your own native language. Or people from the East Coast might want to translate it into East Coast English and so on. And MIT is another special case, right? I mean, anyone who's reading the help messages in Emacs knows that they have a language of their own, right? So now anyway, we try to make the help message in an IU situation, and when you see the new TeX manual with the illustrations, you'll also get an idea that we can sort of personify TeX, because there's a character that appears in these illustrations who is going to be on all our T-shirts next year. Now so this is a simple use of the scanning, and there's a slightly more interesting one on the next page, in case you're getting bored. This one is used to scan a keyword when we're looking for something like plus or minus or for, after, various words that might be present in a text. And this one we'll look ahead to see if you've got if you match a keyword either with uppercase or possibly in an uppercase version of the keyword. It's all done here. Whenever you're looking for such a keyword, this function scan keyword returns yes or no whether it found the keyword or not. If it found it, then we pass it in the input and we're ready to read on. If it didn't find it, we back up over the partial finds that we might have made and are positioned back at where we were before we started. Okay. But after that we get into the interesting things. The really important basic scanning routines are the ones that recognize high-level constructs in the input. For example, if it comes time for TeX to look for an integer number, then TeX can say scan int, and it will look for an integer number as the next thing in the input. Now, an integer number can be an integer number like 12, 1 followed by 2, but it could be an octal. So it would be if the next thing we see is a apostrophe, then we start to say, well, we'll scan in octal notation, and 1, 2 will mean 10. It might start with a backwards apostrophe, which means we're looking for a character constant. But integer number might start with a minus sign, of course. Then we have to have all these options again after we've decided to negate it. In fact, it can start with a plus sign, which is sort of a no-op. And we go past the plus sign, and we can have a bunch of minus signs. In fact, a bunch of minus signs and plus signs there. It's important when you have a language that uses macros to allow minus to appear, because otherwise the macros would have to be very worried about not allowing that to come through. So minus should be legal. But besides all of these things, other integers can also be stored in text registers. So it might say \count something or other, and we're supposed to recognize that and fetch the current value of the counter. The most complicated one is when you say the. In TeX82, this is something that isn't in the present TeX, but if you want to give an integer, you can start it out with the word the. And then the will fetch many things inside of TeX internal tables. So the will be able to fetch out, for example, any one of the parameters, the hyphenation penalty or something like that. The can be used to find out parameters that have been stored with a particular font, and many other things. Now, scan int then scans an integer. There's also scan dimen, which scans a dimension and will return the value of the dimension. Now, as I wrote this, it turned out to be better not to return the value as the value of a function, but to put it in a global variable, curval. And again, here was a case that my original design was not to use this global variable, but I found out later that I was getting much better program by using a global variable for this purpose. So curval is, if you call scan int, the answer appears in curval. Now, so scan dimen is for getting a dimension, and there's scan skip or scan glue. Gosh, I forgot what I called it. Scan dimen starts at 400, and scan glue. Scan glue at 413. So these are three high-level things. The scan glue routine is going to look for something that is a dimension, and then possibly saying plus some other amount of stretchability, and then minus something or other. Well, now all of these three things can say the. For example, when TeX comes to the point where it wants to scan glue, the glue might start with the word the. It might be the baseline skip, for example. So if you want to do a v skip by the baseline skip, you can say v skip the baseline skip. When TeX starts its v skip instruction, it'll call scan glue to figure out how much it's supposed to skip by. So v skip can be followed by the. Now, let's look at the syntax a little bit look at the syntax of glue. What does it consist of? Well, it consists of a dimension, and then optionally plus a dimension, and optionally minus a dimension. So we know that in order to scan these words plus and minus, we're going to have that scan keyword subroutine, and we got scan dimen to do this thing. Well, but now if you think about it, dimen starts with a dimen, like 10 points, starts with scan int. One of the dimensions can also be apostrophe 77 point. You can give a dimensions in octals, so it has to start with scan int integer, or you can say count 5 points, things like that. So dimen can start with an integer, and glue can start with a dimen. And all of these can be the. So when I call the here, okay, if it says the baseline skip, that would substitute for all of this. But if it says the var unit, that's a dimension, or the h size, or v size, say, that's a dimension. That would leave us only at the first part, and then we still have to look for plus again. And the, if it was a count or some other integer register, like the time or something like that, all kinds of integers that can occur. Who would like to v-skip by the time of day, but why not? Then it has to be followed by, then that's only part of a dimension. So after we finish, so we have the subroutines of TeX called scan the, but it doesn't know what it's going to wind up with. It might wind up with glue, a whole piece of glue. It might wind up with a dimension. It might wind up with just an integer. So besides cur_val, which contains the result of scan the, we also have cur_val level, which tells what kind of a thing it found. And so the cur_val level will be set to either int_val or dimen_val or glue_val, telling you what kind of a thing you got. So after you call a subroutine called scan the, and looks ahead to see what's following. And afterwards, if it found a baseline skip, full piece of glue, then cur_val level we'll say glue_val, and cur_val will be a pointer to the specification of the glue that was found, so that you can figure out what you got. That was the main unusual aspect of the design of these particular subroutines. Now, these things are also recursive because if you see what's going on, if you say if you're trying to scan an integer starts with the word count. Then which counter are you doing? You have to give a number between 0 and 255, and that's an integer. So you have scanning an integer can reduce to scanning an integer or scanning the. I mean, you could say count the something or other, and that would give you one of the counters. And so scan the has to call scan int has to call scan the, and scan int, and so on. So these procedures are mutually recursive, but they keep on getting further and further into the input, so they don't get into a loop, of course. Question, yeah.
Yeah, it seems almost that what you're asking it to do there is identical to what you're asking it to do when it expands macros. I'm a little curious about why you didn't do it the same way.
In the get next routine itself.
Yeah, that simply have glue parameters, in fact, be macros, and they have them expand to token lists.
Well, the easy answer is I didn't think of it, but But I haven't got a simple. Otherwise, this is the way that occurred to me to do this. Yeah. Now the. Okay, so I'd like to look at in the remaining 5 minutes. I'd like to look at one of these in a little more detail, so you can get a little more feeling for it. By take a suggestion from the audience. What do you think would be a good one to pursue? Just to get a feeling for what's totally involved here, or you don't want to look at any of them. What? Lynn, tell me. No idea what to do. Okay, well, let's take a look at the details of scanning a domain then. Scan domain starts on module 400, and when we look at what actually has to be done, now the job of scan domain is going to be to put in curval an integer in scaled points, or in other words, a scaled quantity, and the units are 2 to the 16th, 2 to the minus 16th points. And this is supposed to be something that all versions of TeX82 will arrive at exactly the same number. It's quite important to design the language so that it's machine independent in this way. Now, but it turns out there's 3 parameters to this when you start looking at what scan dimension has to handle. And the first parameter is called mu. Because of things in math mode, when you say m skip or m kern to give spacing in math mode, you're not supposed to say 3 points. You're supposed to say 3 mu, which is 3 math units. And this is a variable unit that will change whether or not you're in a subscript or something like that. But math units are not allowed outside of these contexts. And so scan domain takes the first parameter mu, which is either true or false, saying whether the units are supposed to be mu or not. Most of the next parameter to scan domain is called inf, and this says whether or not it'll allow the units to be infinite. There are 3 versions of infinity: fill, philil, and philolil. And if anybody knows a poem by Ogden Nash about a 1L lama is a priest, a 2L lama is a beast, and he bets something that they'll never see a 3L lama or something like that. Well, we don't have 4L fills in this language. But this inf parameter is to scan domain is true or false depending on whether or not such things are legal, and they're only legal after plus or minus. So usually that parameter is false. And the third parameter is called shortcut, and that's because when you're scanning a dimension, you might already have built up part of that dimension, and you're ready to go right to the part that adds up that inserts the points or whatever. And because you might have called and it gave you an integer, and so you're halfway through into your scanning dimension already. So you want to pass by that first part of the routine. So those are 3 parameters to scan domain. Most of the time when I want to get a dimension, though, in one of my semantic routines, I'll call scan domain of false, 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 because all of those other cases haven't arisen. There's no shortcut, no mu, and no infinite glue allowed. Okay, now scan domain is, I'm looking at module 401, and I have a fairly large procedure here, but I think by reading it in this module form, we boil it down to in this case a little more than 12 lines. But we can see exactly what all it has to do. F is an integer is the numerator of a fraction whose denominator is 2 to the 16th. The big problem in scan demand is going to be to preserve this machine independence to make sure I do all my fixed point arithmetic with numbers that would fit on 32-bit machine. And also I have to check for arithmetic overflow that might occur then during these calculations. The Kerr order, this is a global variable that's going to, if I do find infinite glue, I have to tell somebody which kind of fill it was with 1, 2, or 3L. So the Kerr order is going to be normal unless I found some special glue. Negative is something I set false, and that'll flip back and forth if I find minus signs in front of the darn thing. Negative means should the answer be negated. Okay, then, if not shortcut, then I have to do all this stuff, which gets the integer part, or essentially sets up a value in Kerr-val containing the integer part of the dimension, and F is the fraction part of the dimension. By the time I finish this loop, then I've got some integer plus a fraction over 2 to the 16th that's got to be finished up with units supplied and so on. Well, let's look at this first part, which we do in case of a short. Get the next non-blank, non-sign token set negative appropriately. And so this is really going to pass up minus signs and plus signs that might be at the beginning and blanks. Then we have to check if it's the. Or register. Register is what comes up if you say count or dimen, or one of the internal things for one of TeX internal 256 registers. In that case, then we have to do a special thing that either fetches an internal integer or an internal dimension. If we find the whole dimension, like if we find the V size, then we get to go to attach sign because we've got the whole thing in the right units. But if we just get an integer, then we continue on and we have to figure out if it's points or centimeters or whatever. If we didn't have in that other case, we back up the input, get ready to read the token again, and check to see whether it was a decimal point or not. And if it was a decimal point, we have to set decimal radix and in other words, the whole thing might have started with a decimal point. You can say 0.1. You don't have to say 0.1. And if you start with a point, then you're getting into a base 10 thing. If you look at this code, you'll see what happens if a guy just says a decimal point and doesn't say 0 either before or after it, but just a period, and then PT or something like that, and it turns out that that's 0. But I hope people don't use that. Okay, that's the way the thing goes. On the next page, we have one of the prettiest modules, the way it gets formatted by Weave on else ifs, I guess. Anyway, this is where we're just looking for all the different kinds of units that can arise, and we have to convert inches to points by calling a macro here, set conversion, which will takes two parameters, the numerator and denominator, essentially multiplying by 7227, dividing by 100 to get inches into points. This is my definition of a point. I've searched for a standard official definition of what is a point, and not found a pronouncement of the Bureau of Standards or anything like that. The reference sources give more or less significant figures, and the ones that gave the most significant figures were all consistent with this value. So it's a nice simple fraction. I'm choosing it as a definition of an inch to a point. As I wanted to emphasize again, all this arithmetic has been carefully designed so that it will not, it will round well, and it will not go over 32-bit calculations and give a decent answer. Okay, any questions before we break? So these are the routines that, there is one, yeah?
This is a question mainly on the web and philosophy. The getNext shows that you use labels, define labels in one module that aren't actually defined until X number of modules later. Do you find this to be a problem in...
Well, I wish that, yeah, I wish that that was, that Pascal had a better setup for those. But actually what I did with the, is almost all the labels in the program are defined once and for all at the beginning. And I probably have mentioned that in my first lecture. In Module 15, it tells about this. I have labels that are used in ways that are quite common in order to do things. So exit is generally just before the end of a subroutine, and there's done to get out of loops, and found and things like this, continue. And these are used in ways that are always the same as if I had a programming language that supported it. And so there's a few idioms that are used in the programming, and the labels were defined once and for all here. Only a few places will we have a special label like attached sign, and in that case, if you notice, the attached sign was defined in the module, but also carried through in the names of other modules that we're going to go to attached sign. It's very important when you give the name of a module that if there's something funny about the control structure that gets into the name of the module. That was one of the important things we learned about formulating these rules. But most of the things, if we had reprogrammed this to be done with very few go-to statements, it would have turned out, I believe, the program would have been a lot less readable and a lot slower, just because of the way the programming languages are working. And if you don't believe me, we can debate this after class. But that is a firmly held belief of philosophy after doing lots of coding in this form. I tried to have these labels on Module 15 is part of the style of programming that's represented in this code. But for example, exit. I define return to be go to exit. And Pascal doesn't have a return statement, so we just do that. Now that means that I have to remember, when I use a return statement in the procedure, I have to remember to declare the label exit at the beginning and to put it there at the end. It wasn't much of a hassle to remember that, though. Okay, thanks a lot. We'll see you again at 11 o'clock.